All right, I guess we are ready. Happy Friday. Good to see you. Welcome to class. It is Cyclohexane Day, so I'm all dressed up to celebrate. And this whole weekend, you'll be celebrating cyclohexane, I think. Homework 4 will be due tonight. I think we'll finish. Test 2 and the Test 1 in the testing center. Models and scratch paper are okay. If you take your models in, though, make sure they're in a clear plastic bag so they can see in there. They don't like the box or any paper in there. I don't know, but yeah, models are okay and scratch paper. So, and use that. That's always my advice. Use your scratch paper, experiment with some of those questions. We'll talk more about test strategy on Monday, but sample test 1 is there on Learning Suite. I talked to quite a few people already about it, answering questions about it. That gives you an idea of the level of the test, the material, how questions are asked, whatever. 20 multiple choice and 4 or 5 write-on type questions worth 40 points. So that's the same format that you'll see on the sample test there. Any questions on that kind of stuff? I think we're okay. Monday is a review day, so we won't start chapter 5 until Wednesday. But come prepared on Wednesday. Don't take too much time off. This material does move rather quickly, so chapter 5, read ahead as best you can for Wednesday. And we'll be grading on Wednesday. We'll be trying to get that done. And I'll say more on Monday about how we hand the tests back and everything. But yeah, very good. All right, so we left off last time talking about conformations. We looked at butane, propane, and ethane, the rotational freedom around sigma bonds, and that's a hallmark of alkanes, right? They're sp3 hybridized single sigma bonds that allow for rotation because of the symmetry around that bonding interaction, right? The electrons are localized on the axis between the two atoms. So that allows for what we say, conformational freedom at that point in the molecule, okay? This makes some complexity here, right? Especially when we get into cyclohexane and some other bigger molecules where it's an issue. I think these were the numbers last time we were looking at. If you can look up there, so we got 3 eclipsing interactions. That's where the dihedral angle between those two groups is 0. Hydrogen, hydrogen, 1 kcal, hydrogen, methyl, because the methyl's bigger. So sterically, that makes some sense, I think. 1.4 kcals, 2 methyls together, 2.6 kcals. So those are all eclipsing interactions where omega is 0, okay, for the rotation. And then if 2 methyls are gauche to each other, what's the angle there? If they're gauche, we need to talk about gauche butane here in a second. What's that dihedral angle between 2 gauche groups? It's not 0, it's 60. Okay, they're still staggered. So that's the only number up there that's actually staggered. And why is that significant? Because methyls are big enough, okay? If you put 2 methyls 60 degrees together, that's a little bit higher in energy than having them both 180 to each other, okay? Well, let's work some problems here on the board and go through this. Colin, the first thing is to review here anti-butane, right, which is where the dihedral angle is 180 degrees. If you make this Newman projection, right, and look down this bond right here, you'll see this methyl and this methyl are what, 180 degrees to each other, okay? But you can freely rotate. That's actually an infinite number of conformations, right? And we have a potential energy surface that we can actually generate there. But this we call the lowest energy conformation, right? And it's staggered. And the 2 big groups on the end are furthest apart from each other they can get, okay? And then we have the gauche one, where they're 60 degrees to each other. That kind of looks like the eclipsed one too, but no, I'm saying it's gauche, it's 60, okay? And we'll review that with the Newman projections here in a second. But the difference in energy between these two is just what? Methyl-methyl gauche, which is 0.9 kcals. Well, big deal. That's a real small energy difference, right? One calorie, 1 kcal is pretty small compared to the overall energy of the molecule, right? Where you got carbon-carbon bonds, carbon-hydrogen bonds, and other interactions. So we're really talking about very small, subtle effects here. But what about the percentage, let's say at room temperature, what does this 0.9 kcals per mole mean percentage-wise? What percent of the time is it anti? What percent is gauche? Well, it's actually kind of surprising, I think. 85% will be anti, okay, and 15% here gauche. Now, you don't need to worry about the eclipsed ones. They're only there for a fraction of a split second, okay? That's just a transition point over to the next gauche one. But this 85-15, where did I come up with that? Well, it's a Boltzmann distribution. I'll show you the graph here in a second, but all molecules, we can talk about their energy states as a distribution and percentage-wise. And it does depend on the temperature. This is for room temperature, 85-15. All right, let's do the more complicated one right here, which is methyl butane. And I think we've got the numbers on that. And you got models. A lot of people got models, or they borrowed ones from me. So there's some more sets up here if you want to come up and grab one. They're available there. But yeah, snap together your 2-methyl butane. And we're going to look down this bond to begin with and look at the first, staggered confirmation here. So remember what the circle is? That's 2 carbons, the one in the front and the one in the back. And that shows us the angle relationship between the groups that are on those 2 carbons. And that's the bond we're talking about rotating. The other bonds we can rotate as well. But if it's a methyl rotating, those are just 3 hydrogens. That's kind of boring. We did that with ethane, right? But now, down these 2 carbons here, we've got 3 methyls appended. So that gives us a little more interesting story to talk about. And so here's the first one. And notice, energy-wise, what do we have here? Well, it's staggered, so we don't need to worry about the 3 eclipsed interactions. But do we have a gauche? Yeah, right there. So the overall energy of this molecule would be what? Plus 0.9, okay? Everybody see that? The only interactions right here, methyl, methyl, being 60 degrees, so gauche. Make sure you can see that with your model, okay? Looking down the correct bond there and adding up the energies. All right, let's get to the next one. And what we're going to do is keep the groups on the back carbon static. We're going to keep those the same. And we're going to rotate 60 degrees the front groups. So if we do that rotation, we'll have methyl here, we'll have methyl here, and we'll have this hydrogen here. Okay. Now, what about the total energy here? What do we have? We have carbon, methyl hydrogen eclipse, methyl hydrogen, and look, methyl hydrogen. So we have 3 times what here for the energy? 3 times 1.4, and that chart up there, yeah, 1.4, that's for the eclipsing. So what's the total energy here? 4.2 kcals per mole. So that's quite a bit higher in energy, right? So yeah, and this is a transition state down to the next staggered one. And we'll see here, we'll put the chart up in a second, but hopefully you can see where I got that number, 4.2, okay? 3 methyl hydrogen eclipsed interaction. Okay, let's keep rotating the front one here. And what do we get over to? We get methyl up. This methyl comes up here. This one goes over here by 60 degrees. So what do we get? We get this. And what's the energy of that confirmation? Again, you should recognize that's what, staggered or eclipsed. It's indeed staggered. So it'd be a lower energy confirmation. And how much energy does it have relative to the others? Let's see, staggered, staggered. What do we have here? Another gauche. So what's the overall energy here? 0.9, okay. So in fact, they're the same. These 2 confirmations you'd say here, right? Just the one gauche. Yes, please. Yeah. You only need to calculate a gauche if it's 2 methyls or 2 carbons of comparable steric size. We'll use the gauche interaction when we talk about cyclohexane here in a minute too. Okay. So yeah, axial versus equatorial. So people are already looking at that and talking about that. Cyclohexane is the main event, and yes, we'll see gauche again for that. But these acyclic ones, usually we're just talking about methyl-methyl. If it's some other number, we would give that to you. But normally, you know, these suffice. And by the way, these would be on a data sheet for the test. If I have any calculations for these conformations, don't memorize these numbers, know how to use them. That's the key thing. Does that help you out there? All right, let's keep rotating here. So rotate, what, 60 degrees again here. And then what do we get? We get that methyl over there, hydrogen here, and that methyl there. Okay, this is an eclipsed interaction, 0 degrees, dihedral angle. And how many do we have here? Let's see, hydrogen-hydrogen eclipse, that's worth what? 1 kcal. Methyl hydrogen eclipse, that's 1.4. Oh, and here's the big one. Here's the new one. We haven't seen this one yet. Methyl-methyl is what? 2.6. So the total energy here is 5. Oh, so that's probably our highest one, right? That would be the least stable conformation, I think. Let's keep analyzing though and see where we go here. Everybody see where we got that? +5? Just adding up all the eclipse. And then this one here, let's keep rotating around, and then we'll get hydrogen, or nope, methyl. Yeah, there's 2 methyls here on the front, right? Oh, sometimes I just draw a line. Okay, back to staggered, right? And what's the energy here? We need to look at that. Let's see, anybody see gauche interaction there? Yeah, there's actually one here. Is there another one? Yeah, now we have a spot where we have the 2 here. This kind of is like an isopropyl fragment, you could say, kind of straddling that methyl group. So 2 times 0.9. So what is this, 1.8? Yep, for that energy. Okay. All right, let's keep going here, being consistent. If we rotate over here, look, we got methyl right there. We got a methyl there. Oh, and the hydrogen right there. So let's see, what do we have? Hydrogen, hydrogen 1. Hydrogen methyl 1.4, what did we say? And then methyl methyl eclipsing 2.6. 2 bigger groups. So what is this one again? Also 5. Okay, it's really the same as that, right? But let's see, I think if we rotate again, we get back to this point, which is where we started. Okay, so we rotated in 60-degree increments through the whole 360 degrees, right? And it's a pretty thorough analysis, I'd say here, right? Low energy, most of the time the molecule's going to be here. And, you know, what percentage of the time could you say? Some of the time over here, 1.8. What's the difference here? The difference in energy, 0.9 and 1.8. The difference here is 0.9. So again, our ratio is probably similar to anti and gauche butane. For 2-methylbutane, I'd say what? 85% of the time here, and what? 15% of the time here? That kind of makes sense. Yeah, so where am I getting these numbers? Let's look at this back up on the overhead here. Oh, so here's the activity we just did. If you want to go through it again and practice, you can use this page. This will be on Learning Suite also. There's our analysis. That's from a student a while ago who did this, and they did it correctly, I think. Are those the same numbers? Yeah. Okay. Yeah. So, yep. 0.9, 1.8, yep, 5.5, 4.2, and then back to the start. Yep. Okay. And that's a pretty complex analysis, I think. Okay. Being able to use those numbers and come up with that. Here's the theory of how these depend on the ratio. And indeed, if you observe butane in the microwave spectra range, and that's where we get these energy numbers, by the way, microwave spectroscopy. That energy corresponds to the energy barriers of these rotations. It's a very specialized type of spectroscopy. I'm not going to share that with you. We're just going to use the numbers and talk about the dynamics of these molecules. And what you see here, wow, a lot of energy. So that's the color coding. And then the percentages here let me point out the one for us. What was our difference in energy for gauche versus anti-butane? It was 0.9. So right here, you see where I'm pointing the cursor there? So it would be at 0.9. This is the conformational energy difference, 0.9. And then we go up to the green line. The green line is room temperature, 21 degrees C, right? So if we go up to the green line here and intersect, yeah, 85.15. So that's pretty accurate, okay? What if you have a difference of like 3 kcals per mole difference in energy, okay? We'll see that pretty soon with cyclohexane. Even if your room temperature, look at that, it's pretty much 99 to 1, 100 to 1, okay? So it depends on the energy difference and the temperature. If you have more temperature, you can have higher energy molecules, a higher percentage of higher energy molecules. If you're at lower temperature, molecules are lazy, right? They're just like people. If they're cold and sleepy, whatever, they'll tend to populate the lower energy states, right? And so if we're down here at minus 78, which is this blue line, where is that? Yeah, and we've got 0.9 difference in energy. Look at that, that's 92.8, okay? So most of the time they'll be in the low energy anti-conformation. In other words, it's not enough energy to populate the higher state, you could say. So hopefully this makes some sense, and maybe you've seen Boltzmann distributions before. Not all molecules in a collection are the same energy state. There's a distribution of energies, okay? You can keep track of it with an equation. Let me show you that Boltzmann equation. It's pretty simple. It relates delta G to minus, let me make sure I get it right here, minus RT. RT is the gas constant, which relates temperature to energy, times what? The natural log ln of K, where K is the ratio of different molecules you're looking at. So in our case, it would be the ratio of the conformational isomers, 85:15, whatever. T has to be in absolute temperature, Kelvin temperature, okay? So you have to convert it. And I'm not going to make you do this calculation. I like to point out these kind of things to something you may have learned or remembered from Gen Chem. We're not making you remember that. We're making you look at the conformations and maybe estimate differences in energies, okay? That's all there, but I like to show that. All right, let's get into the cyclic ones now. So here we go. We've already looked at the names of these, right? Cyclopropane, cyclobutane, cyclopentane. Oh, and let's stop at cyclohexane because that's the main event. Exclamation point. Okay. Cyclohexane, cyclopentanes are very common in nature and in drugs and different materials. You'll see why in a second. These are cyclic, of course. These are sp3 hybridized. So what bond angle do they want to have there? They want to have 109.5, right? But let's see, cyclopropane, what's that internal angle? Let's see if you remember a little geometry there. What's that internal angle of a regular triangle like that? 60 degrees, right? And here we are talking about theta angles, okay? Not dihedral, which we were just talking about. So that angle, what, 60 degrees? Well, that's a pretty big deviation from 109.5, right? So that molecule is highly strained. It's a high energy molecule. When it combusts, it gives off a lot more energy than normal propane, okay? Because it's tied up as a cyclic ring. Same thing here. What's this internal angle? That's an easy one, right? Even at 8 in the morning, I think you can get that. What is it? 90 degrees. Okay, this one's a little less commonly known, but let's see if someone knows it. The internal angle of a pentagram like that. Cyclopentane, what's that going to be? Pentagon. It's close, 108, I think. Yeah, and so look, that one's really close here. So we'd say cyclopentane is probably strain-free. Now there are some issues that make it a little more strained than this guy. Cyclohexane is the least strained up here. And why is that? This internal angle, though, if it's flat, would be what? 120. So question mark. This bothered chemists early on. They knew 109.5 was the magic angle. That's where things were strain-free, tetrahedral carbon, whatever. And that's what we have here. There's 2 hydrogens or 2 other groups on there, right? But if you look at the flat polygon here for cyclohexane, that's 120. That's an issue, right? That's going to be strained. But is it this guy here? Well, to alleviate that strain, the conformation looks like this, which is your infamous chair. This is the thing that's going to dance in your dreams and in your thoughts and everything for the next couple days to do well here on test 1. Cyclohexane. So why do we call this a chair? And how did this pucker? And this angle right here looks like 15 degrees, not 109.5, right? But this is a sideways view. So let's take the sideways view of the polygon, okay? And let's take this carbon right here and pull it downward. And then take this carbon right here and push it upward, okay? And then what we see, still looking at it sideways here, we'll see this, okay? Now this front edge is coming out at us. And usually the bottom edge of any cyclic structure is the one that's coming out at us. But we need to look at models to really figure this out. And if you got your model kit with up to 6 carbons, get it out and get cyclohexane primed up. You can come up here and grab a couple atoms off these models if you got my simple ones there, and you can put together, because I think originally we only had the 5 atoms for it. But let's look at the flat polygon first. So there it is, cyclohexane. And what do you notice there? Yeah, all of the carbons are in a plane and it's flat. And this internal bond angle right here is strained right now. It's 120 degrees, okay? Doesn't want to stay like that. What it will do, let's grab the end. Oh, look, it did it automatically. I didn't even need to touch it. It doesn't want to stay flat. That's because these bonds right here are locked at 109.5, right? Just like yours in your kit there. So it takes a little bit of work to planarize it. Well, let's pull that one down. So that's the one I just pulled down my left hand. Let's push this one up. And what you see is this, cyclohexane in a chair conformation. Now, why do we call it a chair? Because it kind of looks like a guy sitting there, kicking back, in kind of one of those lounge chairs at the pool, right? And that's what it looks like. We got this one puckered downward, and this one puckered upward, okay? And you see these groups. So let's see here, though. Why did we pucker one up and one down? Well, we could pull this one up and push this one down. The guy will fly off the chair, right? But it'll look like this then. Okay. These are actually in equilibrium with each other, okay? There's a barrier of about 10 kcals per mole between those 2 conformations. But for cyclohexane itself, they look the same, don't they? Who really cares? It's just going back and forth there. But let's look at something a little more detail here. Let's look at the hydrogens that are on here, okay? So you okay with the view? This angle right here is not 15 degrees. It's right here. And if you look at it, it's 109.5 now, okay? This puckering relieves that angle strain. And it also relieves, what do you see on the sides of these carbons? You see the hydrogens bonded there? They're all eclipsed with each other if it's flat. If you go over to the chair, they're all staggered. That's another thing to notice in your models, okay? And let's add those hydrogens in here. So hydrogen here, 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 in the front there, back there. Oh, there's 12 of them. Ouch. There's a lot to keep track of here. 12 hydrogens. Ouch. Let's back up a little bit and do a little artwork. How are we going to draw this chair adequately and be okay at that? You start out like this. Start out with a line like that. Okay, everybody follow along. We're now in art class, by the way. Draw this line up like that. A little bit shorter. It's in the front, whatever. And this line right here. Those three lines now, everything else we draw will be parallel to one of these lines, okay? So that's a sideways view of this puckered down carbon here in my left hand, okay? Down, up, and then kind of a cross there for this one. Okay, let's draw the next line. That's this one. It's parallel to this one over here, okay? It's parallel to the third one over. So that would be this one back here and this one here. And then the next line here, look, is parallel to that one, okay? And then this one here, the last one, look, is parallel to this one in the front. So they're all the same that way. Now, what's different are when we draw in the hydrogens, we're going to draw in some that are axial. And what do we mean axial? And some equatorial. Well, this is kind of like a round object, right? And so the axis is in the top. Here's our axis, okay? Going right down the center of the molecule. All the sets of hydrogens here that are on cyclohexane that are parallel to the axis, we call what? Axial. Okay. So there's our axial hydrogen. Yeah, this is just a convention of cyclohexane. It's an amazing object found in nature, and it's found in so many things, in different molecules, natural products. It's incorporated into drugs. We'll see it in the hormones, the steroids, cholesterol, progesterone, estrogen. We'll see it there in a second. But what about these other hydrogen? Notice I've got this color coded right now in my model. You probably can't do that in yours. But what color are the axial ones that correspond to my model? They're the purple ones, yeah, okay. You see they're all axial there. They're all parallel to each other, parallel to the axis. Okay, what's the other position in a round object like this, around the equator of the object? Are the equatorial hydrogens. And they're parallel to these other lines here. Notice this one here, this equatorial is parallel to that one there. So I'll circle all the equatorial ones. And it's good to go through this sequentially and make sure you can identify all those things. What are they colored here in my model? They're colored green. Okay. All right, now let's do the ring flip. Just when you think you got this figured out. Purple is axial, green is equatorial, right? Okay, follow this now, okay? I just did the ring flip. Purple was axial. Purple's now what? Equatorial. And what? Green was equatorial. Green is now what? Axial. When it does this ring flipping, those positions exchange from axial to equatorial, okay? How it does it, conformationally, maybe we need to say a little bit about that. So let's go through this. So you actually bring one of them down first, and you go to a higher energy flattened state. It's called a half chair, okay? And then you bring it down a little bit further, and you go to what's called a boat conformation. And I'll show you these to you, half chair, boat, and then this one comes up here, you see, and that's what we need to get to, right? The other chair, okay? So that's kind of the progression of the mechanism, we say, of interconverting the conformers. Let's do it a little more slowly. So let's take this one and flatten that one. So there's our half chair, where 5 of the atoms, you see, are all in a plane now. I took the one here in my right hand out of the plane. And then here's the boat. Okay. And the boat kind of looks like a boat. You've got the bow and the stern here, and these two groups are pointing right at each other. That's why it's higher in energy. This is about 10 kcals higher in energy. And it's not only that, it's all these eclipsed interactions on the side. And then it's these flagpole interactions right here, they're called, to keep the boat comparison going there. There's boat. And then what did we get over to? And then the other half chair, and then over to the other chair, okay? Don't worry about that, but it's a significant barrier, 10 kcals per mole. But at room temperature, how much energy do we have available thermally? We have about 20, 25 kcals per mole available, room temperature. So actually, cyclohexane is flipping back and forth about 10,000 times a second, which is an amazing molecular dynamics thing going on, okay? All right, now, if that was it, you know, we wouldn't care too much. But what we really care about is substitution. Let's put a group on here and look at some important changes that go on. So if we've got, let me clean this model up a little bit. Cyclohexane. Let's look at methyl cyclohexane. So here we've got a group on here, okay? Where are we going to put it? Well, let's put it here to begin with. And if we looked at our flat thing to start out with, it'd be like that, okay? And then we pulled this one down and this one up to get to that conformation, okay? And notice we have the methyl group in what position? And it's always good to draw the hydrogen that's also on that carbon. So is that methyl group in an equatorial or axial position? And this is the key thing, right? Can you identify that as axial or equatorial? Let's see, it's parallel to these two lines over here. Here's our axis. Which one is parallel to that axis, the hydrogen or the methyl group? The hydrogen. The hydrogen is axial. The methyl group we say is what? Equatorial, okay? Now let's do the ring flip, and that's happening rapidly at room temperature. And when it ring flips, this one comes up, this one goes down just like before. Here's our hydrogen now. Where's our methyl group? It's right there, okay? So what just happened here? Remember the axial equatorial positions exchange? We're not breaking a bond and putting them on the other side. We're just puckering this carbon in the up position. Notice this is puckered down, so anything that's in the up position there is going to be equatorial. This carbon's puckered up, so if it's up there, this is what? Now axial. Okay, well, what do we notice about this? We have this carbon here, and this carbon over here, and this carbon here. That's a 1, 2, 3, 4. There's a butane interaction, right? Let's see. Before here, we had this, like 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And look, that's what? Anti. Okay? If you look down that certain carbon-carbon bond right here, if you put your eyeball right here and look down at this methyl now is what? 60 degrees to that. That is indeed a gauche interaction. And that methyl over here, if it's axial, is another gauche interaction. Let's see if the model will bear that out. And we need to get a methyl group on here. Here's our methyl group. Okay, everybody see that that purple bond out there is equatorial. Okay, now let's do the ring flip. Okay, and now what? It's up here, it's axial, parallel to the axis. And what do you see? You see this carbon, carbon, carbon right there. And if you look down this bond right here, you see this carbon to the methyl group is 60 degrees. See that gauche interaction right there? You kind of have to look at your models there and see that. But if it's axial, it's going to be closer to these two carbons right here. How much is that worth? 0.9, right? And 0.9. So what about the energy difference between equatorial methyl cyclohexane versus axial methyl cyclohexane? Well, the measured amount is actually 1.7 kcals, which is an amazing number because it's what? Approximately 2 gauche interactions. So these interactions carry over into more complex molecules, okay? That should make some sense, okay? These are consistent numbers. These are similar carbon, hydrogen, type compounds, hydrocarbons, whatever. But everybody see why the axial methyl would be higher in energy than the equatorial, okay? It's kind of hard to see these two gauche interactions, so I'm kind of highlighting those carbons. If you go around this way, you'll see a 60-degree interaction there. Well, you can kind of see it, right? There's gauche butane. In here, 1, 2, 3, 4, you see it as what? Anti-butane, embedded within that molecule, okay? But the overall measured difference in energy between the two, 1.7, and that bears out this, these isolated interactions, okay? So yeah, everybody okay with that? Flipping your models back and forth there. Methylcyclohexane. Let's look at some other groups here. If we have, oh, let's go to a real big one. How about tert-butyl? Well, tert-butyl has the 3 methyls on it. So let's see here. We've got this now. And again, which one is going to be more stable? Obviously, the equatorial tert-butyl cyclohexane. Notice here we have, in addition to the gauche interactions, we have, 3 methyls on the carbon we're talking about here. And these bump right into these hydrogens. If you make your model of that, you'll see we have a steric clash there. And let's see, what's that energy difference going to be for tert-butyl group? Well, I've got it on the chart here coming up. In fact, let's go to the chart here, Colin. Let's go up to the to that. Yeah, there's our cyclic ones. Cyclopentane is an important one to point out. It's 108 if it's flat there, but there's usually 4 carbons in a plane, which makes a lot of eclipsed hydrogen interactions on the side, which makes it a little less stable than cyclohexane, the one we're talking about, which is lower in energy. So these are a couple of the others there to talk about. And strain energy overall, you see here for cyclohexane. So this is the number of carbons in a cycloalkane. And you see cyclopentane is a little higher in energy than cyclohexane. And then they go up here for heptane, octane, nonane. And some of these have destabilizing non-bonded interactions. They don't have the same nice chair conformation that's strain-free for cyclohexane. Cyclohexane is really magical that way. And you see the super high strain one here for what? Cyclopropane and butane, right? Those are those deviations from the theta angle, 109.5. The others kind of taper off, and then kind of a strange thing, you get down here to 17. It's actually a little more stable overall than cyclohexane. Don't worry about that. But here's what I wanted to talk about. This is the important thing. We just did methyl cyclohexane. And what's this A value called? A stands for what? Axial versus equatorial. These are measured energies. There's a couple different ways to experimentally measure these things. I won't get into that, but these are the accepted values for these axial versus equatorial interaction. And it's always the axial one that has the higher energy here, disfavored. And that's because of the gauche interactions there. With methyl, it's just 2 gauches, right? 2 methyl-methyl gauche. Ethyl, a little bit higher. Isopropyl, higher still. That's a bigger group, right? And then tert-butyl, the one we were just talking about. Look at that, 5 kcals per mole. So if you look at the Boltzmann chart there, a difference of 5 kcals per mole energy is 100 to 0, okay? Depending on the temperature, of course, but I can go back to that. But a tert-butyl group is a very big group sterically because it has the 3 methyls right on that carbon, right? A benzene or a phenyl group is pretty big also, right? 3 kcals per mole. An alkyne is really small, an acetylene. So that's on the cyclohexane. That's a linear small molecule. Difference is only about half a kcal. Cyanide also very small. Hydroxyl, it's smaller than even a methyl. It just has 1 hydrogen as opposed to 3 on it. A methyl ether, again, it's got that oxygen spacer there, so it's smaller. A thiol, you think sulfur's a bigger atom, but it's even less than a methyl. And don't worry about these trends or anything. I like to point out the halogens. These are really big atoms, right? Especially bromine and iodine. But look, they're like half a kcal. They're less of an A value than a methyl group. There's a couple things you can point to there. Indeed, they're very big atoms, but what about the bond length? Carbon, bromine, or iodine bond is very long. So the longer you have that bond, the more its steric interactions attenuated. So the A value anyway drops off there. All right, let's get to the cyclic ones here on the board with two groups on it now. And this is the key thing. Here's the hardest concept, I think. We'll probably keep doing this on Monday just to keep going here. So let's look at trans dimethylcyclohexane versus cis. And let's do 1,4 at first. These we called what? Stereoisomers. They're the same constitutional isomer. They're both 1,4 dimethylcyclohexane, the name, right? But the full name here has to have trans in front, and the full name there for that one has to have cis in front. One of these is lower in energy than the other. If you burn both of these molecules separately in what's called a bomb calorimeter and look at the energy or the heat that comes out of that combustion, which is just combining with oxygen to make CO2 and water, they both give the same ratio of CO2 and water, but one is more stable and it gives out less heat, and one is less stable and it gives off more heat. And I won't tell you which is which now, but one gives off 1.7 kcals more than the other. 1.7. That's a number we've already seen before, right? It's approximately what? 2 gauche interactions. Let's look at this guy, the trans one first. And if we put that like this on the flat view and look down at the top, I think you can see this is down and this is up. So that's indeed trans. And let's pucker this guy. Let's push that one down and this one up. What do we get? We get this on the chair now. So I went a little fast there, right? But I think you can keep track of that. Make your models if you need to review some of these topics. Now that's not the only thing right here. We're in equilibrium with what? Bringing this up and this down here. So that'll look like that. And we got that. Which is the more stable conformer of trans 1,4 dimethylcyclohexane? The one on the left or the one on the right, and why? One on the right, why? Yeah, they're both equatorial, okay? Diequatorial. This one would be higher in energy by what? 2 times 1.7, okay? Higher in energy. This one would be the low energy one, okay? But that's just for the trans so far, okay? Let's now do the cis. And we start out with our flat view. So this is what you should do, I think, especially beginning students. Do it sequentially and have your models with you as you work some of these problems. This is a tougher problem, okay? Trying to figure out which one is the more stable stereoisomer, the cis or the trans. You're told that by combustion data, one gives off more heat. Which one is it? Okay. So far, we just looked at one. We've identified 2 conformers here. One that we think is lower in energy, one that would be quite a bit higher in energy. Okay. Now let's do the cis one. We've got up and up. Okay. Notice that's fundamentally different than the trans one. Looking at it flat. I think that flat view is the place to start. Okay. Because if you just jump to the chair, sometimes it's hard to see where things are going to be. Okay. But you can see here that these 2 hydrogens are still trans to each other, and these 2 methyls are still trans, even though they're both equatorial, okay? Because they're at the 1,4 positions, okay? That'll change whether they're 1,2, 1,3, or 1,4 to each other. So here, let's do this one. Pucker it, and if we pull that one down and this one up, what do we get? Get that. Okay. Add the hydrogens in if you need to. Verify that we're still cis. Okay, let's see. Is this an equatorial or an axial methyl? Okay, equatorial, very good. This one axial or equatorial? Axial, good. So yeah, you need to be able to identify that. Draw the axis if you need to. Make sure you draw things carefully. And then let's do the flip here. So that one up, that one down. There we go. And that one. Let's see, is this one, if it was equatorial to begin with, now it's axial. And if this one was axial, now it's what, equatorial. Ah, what are the energy differences here? Axial is plus 1.7, right? You don't need to worry about the A value if it's equatorial, only if it's axial, use the A value. Here, equatorial, now axial, oh, they're both 1.7, okay? So when we burn trans 1,4-dimethylcyclohexane, and we separately burn cis 1,4-dimethylcyclohexane, which one gives off more heat and why? It'd be the less stable one, right? Let's look at the energy. So here we're talking about, burning one and going here to the same level of CO2 and water. And here we're talking about another one that's going to burn and end up at the same place. Okay, which one is the cis and which one's the trans? Which is the more stable one overall? It's the trans, right? So that would start at a lower energy point than what? The less stable cis. And when it burns here, it's this difference in energy, right? The trans one's going to give off less energy because it's starting at a lower energy set point. It's more stable overall. Okay. You could say, well, we had this unstable conformer here where they're both axial. Yeah, but that difference there is over 3 kcals per mole. That's less than 1% at room temperature. The major one, 99 plus, is here. Okay, diequatorial. So that's this point right there. Okay. And then our cis one always has an axial methyl. So that's making it what? Less stable. And then it will give off what? More heat. Okay. So this one here is the one that will give off more heat. This one we say is what? More stable. Now, this is a tricky concept, isn't it? We've got to go through the conformations of the chair cyclohexanes. We've got to keep track of axial, equatorial, and the relative stereochemistry, cis and trans. So things are piling up here. It's a harder type of problem, okay? So you need to practice enough of these to see. Let's do another one here. Yeah, we got a minute. Let's do another one here where they're 1,3 to each other. Let's see. I think working problems, using the A values correctly, being a good artist helps, I guess. How about this here? Let's have methyl down, isopropyl up. And so that's the trans one. Well, let's have methyl up and isopropyl up. Okay, 2 stereoisomers, cis and trans again. Let's draw the depiction here of it. So what do we have? We'd have that methyl down back there and isopropyl what up there. And let's do our puckering. Bring this down. So what do we have here? We have this hydrogen up right there, and what? Our methyl's going to be right there, equatorial, okay? And what? Our isopropyl's going to be up right there. Still trans, okay? That's just one conformation. Let's do the other one. Let's do the ring flipping. Exchange the opposite sides there. Now, what do we get? We've got this hydrogen equatorial, and look, our methyl's down here. And those ones in the back are kind of hard to draw. But yeah, it's still, that position there, just with this coming up there. And then what about this one here? Oh, there's our isopropyl now in what? Equatorial position. So which one is best? Having the methyl equatorial or the isopropyl equatorial? And which one would it be? Well, the A value here for this is plus 2.2 for the isopropyl. The A value for a methyl is 1.7. Let's see, what's the difference in those A values energy-wise? 2.2 minus 1.7, so it comes out to what, about 0.5 difference, which is still significant. I think it turns out to be 75% this one and 25% that one. And again, those numbers, calculations from the Boltzmann distribution, I don't hold you to, but I think you can see the A value difference here, 2.2 versus 1.7. Okay, that's just the trans, right? Let's do the cis. So what do we have here? We've got up and up, okay? Up and away here with chair cyclohexane. So what do we get here? Let's do our thing. There's our methyl up and isopropyl up. Uh-oh, that's a diaxial interaction. That's going to be what, the 1.7 here and the 2.2 together here. So that's what, 3.9, ouch. I hope there's a better low energy conformer to this, and it should be there. Let's analyze it. If we pucker it that way, then we have this one equatorial. Oh, and our isopropyl equatorial. Now notice they're still cis to each other, right? These two hydrogens are down, equatorial, equatorial, axial, axial. Here the two hydrogens were equatorial, equatorial, right? This axial, axial thing is going to be much higher in energy than this one. So this would be the stable one. This is the one that would give off less heat upon combustion because it's less stable, or sorry, more stable. This one's less stable, right, that conformation. But it has a low energy conformation here that would be 99 to 1 or more. And most of the time it would be like that, okay? Yeah, and this difference here, you know, there's always one of these axial, and that's going to be, difference in energy is going to be, this one's a more stable one, but still, it's 1.7 here over this one. So this one will give off less heat, probably by about 1.7. You can't draw too many conclusions about these things when you have multiple A values you're using, but it's amazing how close these energies are to what's actually observed. And I went over, sorry. We'll have a little bit more. I'll show you cholesterol next time, and we'll do redox on Monday. But I think you have enough information now to finish your homework for test 4. That'll still be due tonight, and we'll see you on Monday. Very good. Okay.